Hey guys, today I just want to go through the solutions to the lesson master from 7.6. I know 7.6 is a tough section, and it's weird because the material that's presented in 7.6 isn't really that hard, but what they're asking you to do now is use everything we've done so far in Chapter 7 to put it all together and be able to solve these problems. So this video basically is just going to be going through the solutions of the lesson master. If you're having trouble still with understanding how I'm getting these solutions, you should go back and watch the other videos that we have for this section. The big idea one, that kind of just goes through the lesson from 7.6. The factoring examples has lots of examples for given a higher order polynomial, given a couple of zeros, completely factor it, find all the roots, that kind of stuff. And then the synthetic division with imaginary numbers, that deals with, hey, if you're given a root that's imaginary, how can you divide out those imaginary factors to find the real ones? So take a look at these. It is a tough section, and we're just are gonna have to keep practicing and knocking away at these problems until we see what's going on. And it's really important that you check these out. I'm happy to help you out if you come in before or after school, but the first thing I'm going to ask you is, hey, have you watched all the videos, to make sure that you've put in the time yourself, because it's important to kind of struggle through some of this stuff and try it on your own. So let's get to these problems. So the first one, they give us a polynomial in factored form. It looks like our degree is 1, 2. This one's a double root, so 3, 4. Another double root, 5, 6, 7, 8, 9. This is a ninth degree polynomial, and they just want to list out the roots that have the different multiplicities. So the roots that have a multiplicity of 1 are going to be the ones that have no exponent at the top of their factor. So if we looked at this first factor, we have x minus root 6. The number I would plug in for x here that would give me 0 would be just square root of 6. And then over here, to get this to cancel out, I would need a negative square root of 6. So those are the zeros that have that multiplicity. And the multiplicity of 2, it looks like 2 plus I, and oh, they were a little bit sneaky with this. So 2 plus I, and then the conjugate roots theorem tells us that 2 minus I should also be a root, and it would have to have the same multiplicity. What they did here was, instead of writing x minus, they changed it to x plus. So this would be x minus 2 minus I. And then they just distributed out the negative and changed it to a plus. But that's what that factor is right there. So also multiplicity 2 minus I. So conjugate roots theorem holds true there. And then the only one of multiplicity 3 would be 9. When you plug 9 in here, 9 minus 9 is 0. And we have that third multiplicity. So those are the zeros with each multiplicity in this example. Next up, they give us a p of z here. It looks like it's a fourth degree polynomial, and it has all real coefficients. And what we learned in 7.6 is that if it's a fourth degree, then we have to have 4 roots. So what they're doing here is they're going to give us some kind of information. They tell us that 2 plus I is a 0. So they want us to verify this, to check it out. So what we have to do to verify, and also I think I mentioned in class, but I may not have, this should be a z right here. It shouldn't be an x. That's a mistake from the printing. So let's take a look here. So we're going to try 2 plus I and see if it's a 0. I'm going to use this whole slide to do that. On the next one, I'll do part B. So z to the fourth, so that would be 2 plus I to the fourth power, minus 2z cubed, 2 times 2 plus I to the third power, plus 2 times 2 plus I squared, minus 10 times 2 plus I, plus 25. So this is a really good review in multiplying complex numbers together, because we're going to have to do a lot of expanding here. So I'm going to kind of use building blocks here. So we have 2 plus I. I'm going to do 2 plus I squared right here. So that would be 2 plus I times 2 plus I. And we multiply that together, we FOIL it here, so we'll get 4 plus 2I plus 2I again, and then plus I squared. Well, I squared is negative 1, so 4 minus 1 is 3, and then plus 4I. So that is 2 plus I squared. We're going to use that a couple spots right here, and then I'm going to use it also to get to the fourth. But let's do cubed first, because we're going to need that. So cubed, I'm going to take that 2 plus I squared. So 2 plus I cubed is going to be 2 plus I squared, and then one more 2 plus I. So I'm going to take 3 plus 4I, and then multiply it by one more 2 plus I. So it looks like that'll give us 6 plus 3I, plus 8I, and then plus 4I squared. Again, I squared is negative 1, so we have negative 4 here, and 6 are 2 plus 11I, it looks like. And then if we do it to the fourth power, we'd have to multiply that one more time by 2 plus I. So 2 plus I to the fourth is going to be 2 plus 11I times one more 2 plus I. and that would be 4 plus 2i plus 22i, and then plus 11i squared, which is minus 11. So this would be negative 7, looks like plus 24i. Okay, so we have our 2 plus I squared, cubed, and to the fourth. Now I'm just going to plug those in here. So 2 plus I to the fourth, we just found out was negative 7 plus 24i. Okay, so that's our 2 plus I to the fourth. Now we're going to subtract 2 times 2 plus I cubed. 2 plus I cubed is 2 plus 11i. So we have 2 plus 11i. And then we have plus 2 times 2 plus I squared. That's our 3 plus 4i. And then minus 10 times 2 plus I. I'll just leave that like that for now. We'll distribute all of them on the next one. And then plus 25. So we're going to hope that this gives us 0, because we're trying to show that 2 plus I is a 0 of this polynomial. So let's see here. So we have negative 7 plus 24i minus 4 minus 22i, right? Because we have negative 2 and then times 2 and then negative 2 times 11i. Then we'll have plus 6 plus 8i minus 20 minus 10i, and then plus 25. Now we're going to cross our fingers and see if this works out. So let's get all of our constants together. So we have negative 7 minus 4 plus 6 minus 20 plus 25. So those are all our constants. That would be like our A. Now let's look at our i's. So we have plus 24i. That's our 24i. Minus 22i. Plus 8i. Minus 10i. So we should get 0 for both of those. Let's see. Negative 7 minus 4 is negative 11. Plus 6 is negative 5. Minus 20 is negative 25. Plus 25 is 0. 24i minus 22i is 2i. 2i plus 8i is 10i. Minus 10i makes 0i. So we have 0 plus 0i, which is 0. So we have proved that 2 plus I is indeed a 0. That was a lot of work, but it all paid off, and we ended up getting 0. So now, we want to find the remaining zeros of P. So before I go on to the next slide and do that, let's just think about what we've got so far. Let's use maybe green. So let's make a list of our zeros. So far, I know 2 plus I is a 0. Now, what does conjugate roots theorem tell us? Well, conjugate roots theorem tells us if 2 plus I is a 0, 2 minus I better be a 0 as well. So we have 2 zeros. It's a 4th degree polynomial, so we're missing 2 more zeros. And we're going to have to figure out what those are. So what I've got so far, and I'm going to put this on the next slide, I think, is that I know this polynomial P of z is equal to, go back to our blue, I think that's a nice color. So we know it's equal to, right now, we have x minus our first root, x minus, in parentheses, 2 plus I. I know that's true. I also know we have x minus 2 minus I. So we have 2 factors, but it's a 4th degree polynomial, so there are 2 more factors that are missing. And I don't know what those are. So to find them, I'm going to take my polynomial and divide by these guys right here. I guess I could use z. I think I'm going to stick with x, but it doesn't matter what variable you use, right? So I know that when you multiply these two together, I'm going to get some kind of a quadratic polynomial, and I'm trying to figure out what these last 2 factors are. So what I'm going to do, we have 2 options here. When I have this 2 plus I and the 2 minus I like to just multiply these together now and get a quadratic, and then I'm going to use long division. So let's multiply these together. So I have x squared, and then it looks like I'll have minus x times 2 minus I. I'm just going to leave it in parentheses for now. And then I'll have minus x times 2 plus I. And then I'll have plus, these are conjugates. When we multiply conjugates together, we get the first thing squared plus the second thing squared. 2 squared is 4 plus 1 squared is 5. So I'll have plus 5 at the end. Okay. If you're having trouble with that, you can go back and review your notes on multiplying complex conjugates, right? When we multiply complex conjugates together, the whole point is the i's go away. So, and then we have these last 2 factors that I don't know yet. So, if we put this together, we have x squared minus 2x. I'm going to write this right above here in a different color, maybe. Let's use red. So we have minus 2x. Whoop, it didn't change colors. There we go. So we have minus 2x, and we have plus xi. And then here we'll have minus 2x minus xi. Those xi's will cancel. So we have minus 4x altogether here. I'll put that in red, that's okay. So minus 4x is what came from those 2 middle terms, and then I have plus 5. And that's multiplied by whatever these other 2 factors are to get me P of z. So what I'm going to do is divide p of z, or p of x, by this polynomial. I'll use long division, and that'll give me the resulting quadratic that I'll have to factor. So we're putting x squared minus 4x plus 5 into x to the fourth. I'm just going to use x's here. You could use z's if you want to. Doesn't matter. Minus 2x cubed plus 2x squared minus 10x plus 25. So x squared and x to the fourth is x squared. Multiply down, we get x to the fourth minus 4x cubed plus 5x squared. Subtract that whole thing off. X fourths cancel. Negative 2 minus a negative 4 is a positive 2x cubed. 2x squared minus 5x squared is negative 3x squared. And we'll bring down a negative 10x and the plus 25. To x squared into 2x cubed is 2x. Multiply down, we get 2x cubed minus 8x squared plus 10x. All right, plus 10x, yep. Subtract that off. Crossing our fingers, we get 0 here because this should be a factor. So we'll see. 2x cubes cancel. Negative 3 minus a negative 8 is a positive 5x squared. Negative 10x minus negative 10x again is negative 20x. And then plus 25. Lots of 5s here, so this is looking promising. So x squared times 5x, times just 5, is 5x squared. So we have 5x squared minus 20x, good, and then plus 25. Hey, check it out. It goes to 0. That should happen because this should be a factor. They told us this is a 0, so that means conjugate roots theorem says 2 minus I has to be a 0. So when we multiply them together, we divide, and we end up with a remainder of 0. So at this point, I know p of x, changing it to x, is x squared minus 4x plus 5 times x squared plus 2x plus 5 with no remainder. So to find the remaining zeros, I have to be able to factor this, or at least find those zeros somehow. Well, it's a quadratic, so it looks like I can't factor this. There are no factors of 5 that add to 2. So I'm going to have to use quadratic formula, which I know is a pain, but it's what we have to do. We have a quadratic. We could find zeros by factoring or by using quadratic formula. And unfortunately, in this case, we can't factor, so we have to use quadratic formula. So we have a, b, and c here, 1, 2, and 5. So I'll do negative b plus or minus the square root of b squared minus 4ac, which is 20, all over 2 times a, which is 2. So that gives me negative 2 plus or minus the square root of negative 16 over 2. That's negative 2 plus or minus 4i, all over 2. So that looks like negative 1, because I'm dividing by 2 on both of these, plus or minus 2i. So at this point, we've actually gotten all of our zeros. If we think about our list of zeros that we came up with already, we had the conjugate roots theorem tell us 2 plus I and 2 minus I are both zeros, and now we have our last 2. So I'll put those in green again, maybe. So our list of all of our zeros, 2 plus I, 2 minus I, which we saw in our first 2 factors up here, and now we have negative 1 plus 2i and negative 1 minus 2i. So if you graphed this, it actually would have no zeros. I don't know, it looks like it'd probably be all above the x-axis. There'd be no real zeros at all, but there are 4 complex zeros. So our last 2 factors, if we wanted to put them in here, would be x minus negative 1 plus 2i and x minus negative 1 minus 2i. Cool. So, tough problem. The next ones aren't so tough. The last 3 we come to will be kind of like this, except they aren't all complex numbers. So this one was tough because they were all complex. So let's take a look at the next problem. How many zeros does this function have? Well, fundamental theorem of algebra tells us that if the degree is 9, there are 9 zeros. Okay. A lot of those will be complex because there's an I in here involved. So not and very many real zeros. In fact, we're going to find out right now how many there are. So how many of those zeros are real? Well, notice that this shares in common an r. So I can pull an r out. So I have r times 6r to the 8th minus I. So now think about this. For sure, 1, 0 we have. These are factors, right? So r is a factor, and so is 6r to the 8th minus I. So if r is a factor, then r equals 0 is for sure a 0. So r equals 0 is one of our roots, or our zeros, or our x-intercepts. Root, singular, because it's just 0. And so we know that there's at least one real 0. Now the rest of them, think about this. We're doing 6 times r to the 8th, and they have to equal I to make this 0. We would have to have 6r to the 8th is equal to I. Well, there is no real number that you can take to the 8th power and multiply by 6 that will give you I, because every real number that you put in here for r will give you a real number. So all the rest of those must be imaginary. So there are 8 complex roots. So there is just one that's real, and that's 0, and then there are 8 complex ones, because they have to give you an I somehow. And the only way you can take something to the 8th power that gives you an I is if they're complex to start with. So a little bit of a conceptual idea there, but not too bad. Okay, so true or false? Those are fun. So let's see here. We have 2 minus 3i. They tell us it's a 0 of this polynomial, x cubed minus 3x squared plus 9x plus 13. Well, fundamental theorem of algebra tells us that because this is a cubic, there are 3 zeros, counting multiplicities. Okay, so we know there are 3 zeros, and they tell us 2 minus 3i is one of the zeros. This has real coefficients, so conjugate roots theorem applies. So if we make a list of our zeros, we know 2 minus 3i is a 0. Conjugate roots theorem tells us 2 plus 3i must be a 0. So we already have 2. So we only have one more 0 left. Well, think about it this way. If it was 3 minus 2i, because these are real coefficients again, what would also have to be a 0? 3 plus 2i. But we only have room for one more. So 3 minus 2i cannot be a 0. So this is true. Because that last one is going to have to be a real number. It can't be a complex number. If it were, then we would have a 4th, and it's only a degree 3 polynomial. So that can't be a 0, because we can't have these 2. We can only get one more. That wasn't too bad. It is possible for the graph of a 3rd degree polynomial with real coefficients to intersect the line y equals -5 exactly twice. So this is getting back to the wiggliness theorem. So remember, the wiggliness theorem told us that if you have a function like this that crosses a horizontal line a certain number of times, this crosses once, twice, 3, 4 times, so that degree has to be at least 4. So here we have a 3rd degree polynomial, so some kind of x cubed plus a bunch of other stuff maybe. But if we think about the line y equals -5, 1, 2, 3, 4, 5 right there. So they're saying, is it possible that it crosses exactly twice? Well, what the wiggliness theorem says is that if it crosses 2 times, the degree would have to be at least 2. This is a 3rd degree, so we should be able to make a 3rd degree polynomial that crosses or touches that line twice. So what I would suggest is we can't, if it was like a regular cubic, that goes through 1, 2, 3 times. Is it possible to move this up or down until it just touches twice? I think we can. What if we did this? So let's say this is our -5. If we just scooted it up until this guy just touches that line. So it looks something like this. So it would touch, go up, and then back down. Now it touches once, 2 times. So this over here would be like a single root. Right? We talked about multiplicities on Friday. This guy over here would be a double root. So we have a single and a double, but because it just bounces there, I mean, it's weird to think about these as roots because they don't go through the actual axis. But it's still, you can think about it as being like a root if you were to move it up by 5. So this -5 down here, it is possible to cross it exactly twice, or to touch it exactly twice. Yeah, so that one is true. So both of them were true. It's possible to touch that exactly twice. Okay, so now for these, this is where we're really going to get into using some synthetic and long division and being able to find some zeros by graphing. So they tell us to first graph it to find all the real zeros, and then we're going to have to factor it to find the non-real zeros. So I went ahead and graphed this on my Inspire, and you can do the same. And we have it right here. So this is what this graph looks like, x cubed minus 6x squared plus 13x minus 10. It looks like it has exactly 1 0 right there at 2. So we're going to make a list of our zeros. Right now, I know that 2 is a 0, so I'm missing 2 of them, and they're going to be complex because we don't show up on our graph. So at this point, I know f of x is equal to x minus 2 multiplied by some other quotient. And to find that, I'm going to divide. So I'm just going to divide f of x by that x minus 2, and it's going to give me, it should give me a quadratic over here. And we're going to have to use quadratic formula to be able to find those last 2 zeros. So I've got it set up again on the next page. So we got f of x here. We know it's x minus 2 times something. And you know what? I'm going to use synthetic division because it's just, I'm going to divide by x minus 2. To find that something, I'm going to divide. So I'll do f of x over x minus 2, and I'm just going to use synthetic division. So 2 goes into the box. We have 1, -6, 13, and 10. Draw our line. 1 comes down, times 2 is 2, plus negative 6, negative 4, negative 8, 5, 10, what did I do? Negative 2 times, what did I do? 2, negative 4, negative 8, 5. Oh, it's negative 10. Fransky. All right, so we have 10 here, and we add them together. It gives us a 0. So at this point, I know that this thing right here is this polynomial. It's x squared minus 4x plus 5. I'm just even going to put it in the parentheses because we know that that's what it is. It's x squared minus 4x plus 5. Now, we could use the quadratic formula to find those last two factors, because really what I want is I want f of x equals x minus 2. I want to know what those last two zeros are. So to find those, we would have to factor this. But we can't factor this because it looks like we can. It's tempting to do x maybe minus 5, x plus 1. That would get us the negative 4x, but negative 5 times 1 is negative 5. So that's not going to work. This actually is going to give us complex roots. We know that because we didn't have any other zeros on the graph. So the complex roots here we could find by using quadratic formula. But actually, if you look back a few problems, so I have to go back quite a ways here. Here we are. So we actually saw that this, where is it? X squared minus 4x plus 5, that came from 2 plus I and 2 minus I. So I'm just going to grab those. So 2 plus I and 2 minus I are our last zeros. So 2 plus I. So we make our zeros list again. We have 2, 2 plus I, and 2 minus I. Because the factoring of this we saw from a problem before is, I need some more space here, x minus 2 plus I times x minus 2 minus I. That's it. So again, you could use quadratic formula here. I might as well just show it. Negative b plus or minus square root b squared, which is 16, minus 4ac, that's 20, all over 2a, which is 2. So that's 4 plus or minus the square root of negative 4, which is 2i, over 2, which is 2 plus and minus I. Okay, so I kind of stole this from a previous problem. I just wanted to show that the quadratic formula does work there. So we have our zeros, and that's all they asked us to do. Factor f of x to determine all non-real zeros. So here's our factoring, and here are our non-real zeros. All right, moving on. So here we have our function, and it's going to do the same thing. So first we graph it. And this is an interesting one because it looks like it bounces off right there at 2. So we might have a double root there at x equals 2. And we can actually even kind of prove it because if it's a 4th degree, if we make our zeros list, here, then we know that 2 has to be a 0. But when we get a complex root, so this first one's going to be complex, then we have to get another one that's the complex conjugate. So we have those two complex roots. I can't have a third complex 0 because then I would get another 0, which would mean I would have 5 in total. So I have to have another real one, and since it bounces off there, it looks like 2 is a double root. So sometimes you'll see people list 2 twice so that you really see that there's 4. But to find those complex roots, I'm going to have to do some long division. There's some synthetic division here. So right now I know f of x is x minus 2 twice. So I could write it as squared, and there's going to be something left. Or you could write f of x equals x minus 2 times x minus 2 times whatever's left. So I'm going to have to divide by x minus 2 and then divide by x minus 2 again in order to find out what that resulting polynomial is. You could also do what we did at the beginning. You could multiply these two together, which would give you x squared minus 4x plus 4. And then do long division to get that number. I'll let you try that on your own if you want to, but I'm going to do it with synthetic division. So we have our f of x here, and I know it's x minus 2 times x minus 2 times some other polynomial. So to find that, I'm going to do synthetic division twice. So I'll put 2 into the box. I've got 1, negative 6, 14, negative 16, and then 8. Draw our line. 1 comes down, times 2 is 2, negative 6 are negative 4, negative 8 and 14 are 6, times 2 is 12, gives me a negative 4, negative 8 gives me 0. So at this point, I've only divided by x minus 2 one time. I haven't done this second x minus 2 yet. So right now, I have f of x equals x minus 2 times this resulting cubic, x cubed minus 4x squared plus 6x minus 4. That's where I'm at right now. But I can still pull another x minus 2 out of this guy. So I'll just put another 2 in the box, and I'll use this guy. So 1 comes down, times 2 is 2, negative 2 times 2 is negative 4, gives me a 2, times 2 is 4, gives me 0. So now I've pulled out that second x minus 2 out of this guy. There's an x minus 2 factored in here that I can pull out. So now I have f of x is x minus 2 times x minus 2 times x squared minus 2x plus 2. Okay. So now this guy, once again, can't factor that. Going to have to use quadratic formula. So if I think about my zeros list, I have 2 and then 2 again, because that was my double root. And now I need to figure out what the factors are hiding in here. So do negative b plus or minus the square root of b squared minus 4ac, which is 8, all over 2a, which is just 2. So we have 2 plus or minus, this is the square root of negative 4, which is 2i over 2. So that's 1 plus or minus I. So my zeros are 2, which is a double root, and then 1 plus I and 1 minus I. So if I were to put these in factored form, I would have f of x equal to x minus 2, x minus 2, x minus parentheses 1 plus I, and x minus parentheses 1 minus I. Because now if I put any of those 4 zeros in for x, it'll cancel out. 2 will cancel out here or here. If I put 1 plus I right here, then I subtract it, it's gone. And 1 minus I right here and subtract it, it's gone. So we found all the zeros. One more. So once again, we have a function here. We're going to graph it. I've got the graph right here. So if we look at our graph here, it looks like our zeros are negative 3, negative 2, and negative 1. So I'll start a zeros list. Zeros, negative 3, negative 2, and negative 1. But fundamental theorem of algebra says since it's a degree 5 polynomial, there have to be 5 zeros. So we must be missing 2 complex zeros. So if I were to start factoring this, I have f of x is x plus 3, x plus 2, x plus 1, and then I'm missing something else here that's probably going to be a quadratic. So once I factor that, it'll be able to give me 2 more factors that are probably going to be complex. In fact, they have to be, because I have these guys right here that are just my 3 real zeros. And then I'll have my completely factored form. So let's see here. So we have plus 3, plus 2, and plus 1. So this is x plus 3, x plus 2, x plus 1, and I'm looking for the last quadratic here, and I'll fill that in after I find it. So once again, you could multiply these to get x squared plus 5x plus 6, then take that, multiply by x plus 1 to get a cubic polynomial, and do long division. I'm going to choose to do synthetic division 1, 2, 3 times, just because it's going to be faster. So I'll put negative 3 into the box, because we're dividing by x plus 3, and then I have 1, 10, 41, I'm getting big here, 86, 90, and 36. But we should get 0 for a remainder because it's a factor. And negative 3 is a 0. So 1 comes down, times negative 3 is negative 3. That gives me 7. Times negative 3 is negative 21, gives me 20. Times negative 3 is negative 60, looks like, 26. Times negative 3 is negative 60, and negative 18, that's negative 78. Sheesh. That gives me a positive 12. Oh, good. Times negative 3 is negative 36. So, and add those together gives me 0. So at this point, I have f of x is equal to x plus 3, because all I've done is divided by x plus 3, times x to the 4th plus 7x cubed plus 20x squared plus 26x plus 12. But there's still an x plus 2 and an x plus 1 hiding in here that I have to pull out. So let's just use those same coefficients with a negative 2. So negative 2 is coming now, so 1 comes down, times negative 2 is negative 2, times 7, plus 7 is 5, times negative 2 is negative 10, gives me a 10 here, times negative 2 is negative 20, that gives me 6, times negative 2 is negative 12, that gives me a 0 remainder. So at this point I have f of x equal to x plus 3, x plus 2, and now what I have left is x cubed plus 5x squared plus 10x plus 6. And what's still hiding in there? In that in the cubic polynomial, I still have a plus 1, an x plus 1 hiding in there that I can pull out. And something to note here, you could do this in any order. If you did x plus 1 first, and then did x plus 3, and then x plus 2, it doesn't matter. You can do it in any order, it's going to end up giving you the same answer. The intermediate polynomials here would be different, but you'd end up with the same thing. So we're going to throw a negative 1 into the box. 1 comes down, negative 1, 4. times negative 1 is negative 4. Gives me a positive 6, negative 6, and a 0. So excellent. Now we have f of x is x plus 3, x plus 2, x plus 1, and now we're left with this quadratic, x squared plus 4x plus 6. And the goal is to get a quadratic because then we can use quadratic formula, or maybe if we're lucky we can factor, but in this case we can't. So that was what we were trying to find, was that x squared plus 4x plus 6. And now we're going to use quadratic formula to find out what the zeros actually are. So we have our zero list over here. Negative 3, negative 2, negative 1. We're looking for those two complex ones. Let's see what we've got. So if we use quadratic formula on this last quadratic polynomial here, we'll have negative 4 plus or minus the square root of b squared, which is 16, minus 4ac. Well, that looks like it's negative 24, so minus 24, all over 2 times a, which is just 2. So we simplify that. Looks like negative 4, ooh, yuck, plus or minus the square root of negative 8. You know, that's not fun. All over 2. So root negative 8, there's going to be an I there for sure. And I can also pull a 4 out of that. So the square root of 8, that's the square root of 4 times the square root of 2, which is the 2 times the square root of 2. So we have here negative 4 over 2, which is negative 2. And the root negative 8 is going to be a 2i root 2. And the 2's will cancel, so it'll be plus or minus I root 2. Ugh. So those are our last zeros. We have negative 2 plus I root 2 and negative 2 minus I root 2. Complete factorization. F of x is x plus 3, x plus 2, x plus 1, and then we would have x minus negative 2 plus I root 2, and x minus negative 2 minus I root 2. And that is our complete factorization. And I think that was the last problem. So hopefully this was helpful for you guys. If you need to go back and look through some of the work that I did on any given problem, that'd be a good idea. So altogether, it looks like this took me about a half hour to do. And I know that might be longer than some of the other homework assignments have taken you, but you got to practice this stuff. You have to try it. So if you have any questions, please let me know. And if you watched this in class while I was gone, I will see you guys back here when I get back. I'll talk to you soon. Bye-bye.